Hello everyone. In the fifth lecture of colligative property in the chemistry of dilute solutions, our today's topic is depression of freezing point. Here in the graphical presentation of vapor pressure against temperature, we can see here three curves, but actually here are four curves. One is AO, another is OC, the third one is AB, and the fourth one is BD. So AB and ABO are actually two different curves which are not being separately visible here in this picture. We cannot distinguish them because they are merged with one another. So let's discuss what about these curves. Okay, ABO, that means this curve, A along B to O. Okay, so this curve is actually the sublimation of pure solid. Suppose pure ice is undergoing sublimation, then the vapor is produced and the corresponding vapor pressure with respect to increase in temperature, the graphical presentation of its change is represented by this curve ABO. Okay, now AB, what about this another curve AB? This is also the sublimation of the solid, but which solid? It is not the pure solid. It is actually the solution which has solidified after freezing. But the interesting fact is that solution, when become a solid, it freezes before this temperature. Before this temperature, T0. T0 is actually the freezing temperature or the melting temperature of the pure solvent. This is O, is the melting point O, and the corresponding temperature is T0. On the other hand, these two curves are similar with the curves as shown in the previous lecture where we discussed the elevation of boiling point. There it was clear that the vapor pressure of the solution is always less than that of the solvent, pure solvent. So here also same thing, the same curve is repeated here, but when you move towards lesser temperature, that means you move to the colder region at a certain point O, where the temperature, corresponding temperature is the melting temperature of the pure solvent, that particular solvent would freeze and it would become a solid. That means it will solidify, and in that case the corresponding vapor pressure decrease would be more steeper than that of the corresponding solvent. But in case of the solution at that particular temperature T0, still that solution would not freeze. It will remain as in the liquid form. In order to get the solid form, the solution has to move further, because actually if the substance is in the pure form or is in the impure form, in the solid form there is no change in vapor pressure takes place, because the surface area, the exposed surface area, there is no effect on the exposed surface area whether it is a pure or impure substance if it is in the solid form. But in case of the liquid, as you have seen in the bell jar experiment, you have seen that the effective surface area or the exposed surface area is blocked by the solute particles, which are in turn non-volatile. So the effective surface area decreased. As a result, the vapor pressure also decreased, which things are already discussed in case of lowering of vapor pressure or elevation of boiling point. But in case of solid, if the solid is made from the pure substance or if it is made from the solution, so in the solid form it doesn't matter whatever it is, and its vapor pressure would remain unaffected for being impure. So the vapor pressure curve of the solid, whether it is in the pure form or it is in the impure form, would remain unchanged. That is why there are two curves which are indistinguishable. One is ABO, the solid of the pure substance, and another is AB, the solid of the impure substance, that is the solution. Okay, so that is why you find there is a decrease in freezing point of the solution, and this difference is actually delta TF, that is depression of freezing point. Okay, so what about OC? You know about this, it is the vaporization of pure solvent. What about BED? It is the vaporization of the solution. Okay, and you have to mention that AB and ABO, maybe they are two different curves, but they are collinear, they are indistinguishable. And at O, the pure solvent freezes, where the corresponding temperature is T0 and the corresponding vapor pressure is P10. On the other hand, the solution freezes at B, where the corresponding temperature is T1, which is less than T0, and the corresponding vapor pressure is P1. Okay, and the vapor pressure of the solution at T0, at this temperature where the pure solvent freezes but the solution doesn't freeze, the solution must have some vapor pressure, and that corresponding vapor pressure is P1S. Okay, so at this point E, the corresponding vapor pressure of the solution is P1S. Now let's derive the equation. So let's recall the Clausius-Clapeyron equation first. The original equation is natural log of P2 by P1, that is the final pressure by initial pressure, equals to heat of sublimation, the molar heat of sublimation, that is delta H sub, divided by R into 1 by initial temperature minus 1 by final temperature. Let's apply the Clausius-Clapeyron equation, that means this equation, for sublimation of solid along BO curve. Okay, so what about the BO curve? Let's reproduce the picture here. When you are taking the note, you need not draw this. Just for my convenience, I am drawing it here. So the curve is BO. So here B and here is O. Okay, so along the BO curve, what happens along the BO curve? Now at B, temperature is what? T1, pressure is what? P1, and at O, temperature is T0 while pressure is P10. So let's put vapor pressure is P1 at temperature T1 and vapor pressure is P10 at temperature T0. Okay, and in the Clausius-Clapeyron equation, in place of T1 we shall write T1, and in place of P1 we shall write here P1, but in place of T2 we have to write here T0. On the other hand, in place of P2 we have to put P10. So here, fine, look, in place of P2 P10 is appearing, and here in place of T2 T0 is appearing. On the other hand, T1 is T1, P1 is P1. Okay, and here delta H of sublimation. Okay, and on processing this equation we find the difference here, T0 minus T1. So T0 minus T1, T0 is greater than T1, so T0 minus T1 is a positive quantity, and that is actually delta TF, that is depression of freezing point. So here in place of T0 minus T1 we are writing here delta TF. Okay, and here in place of T1 T0 we have again made the approximation, since there is the difference is very little, so T1 into T0 is almost equal to T0 squared. Okay, and this is equation number 1. So remember this equation number 1, this is natural log of P10 by P1 equals to delta H sublimation by R into delta TF by T0 squared, where T0 is the freezing point of the pure solvent. Now let us apply the Clausius-Clapeyron equation for vaporization of the liquid along BE curve. So let me again reproduce the diagram here for my convenience. You need not do this. So BE, here is the point B, here is the point E, and this is definitely for the solution. And for the solution, at the point the corresponding temperature is T1 and the corresponding vapor pressure is P1. On the other hand, at this point E, the corresponding temperature is T0 while the corresponding vapor pressure is P1S. So let's write them. So vapor pressure equal to P1 at temperature T1 and vapor pressure is P1S at temperature T0. Okay, and now again put this in the Clausius-Clapeyron equation similarly. So this way we get natural log of P1S by P1 equal to delta H vaporization. Here in place of delta H sublimation we are writing delta H vaporization, because we have applied this for vaporization of the liquid, because this curve is actually the vaporization curve of the solution, BED curve. Okay, here it was sublimation curve, BO was the sublimation curve, but BE is the vaporization curve. So that is why in here we wrote delta H sublimation, but here we have to write delta H vaporization. So by similar processing we get this relationship. As a result, we get equation number 2. So what is equation number 2? Now equation number 2 is natural log of P1S by P1 equals to delta H vaporization by R into delta TF by T0 squared. Now we have to subtract equation 1 from equation 2. In the left hand side of equation 1 we have this one. In the equation 2 we have this one. And in the left hand side of equation 1 we have this parameter. Okay. And in the right hand side of equation 2 we have this parameter. And in the right hand side of equation 1 we have this term. So what is the result of subtraction? The result of subtraction is ln P1S by P10 equals to delta H vaporization minus delta H sublimation by RT0 square into delta TF. Now just multiply both sides by -1. If we multiply both sides by -1, then in the numerator we can just interchange their positions, like delta H sublimation minus delta H vaporization. And here if we multiply with -1, then these two terms would reciprocate. That means P1S by P10 would become P10 by P1S. Okay, so here we write here ln P10 by P1S equals to delta H of sublimation minus delta H of vaporization. Actually, according to the behavior of additive nature and according to the Hess's law of thermochemistry, the second law, it is actually the difference between two is delta H of fusion. Okay, and finally we get the relationship delta H of fusion by RT square into delta TF. Okay, and similarly the ln P10 by P1S is nothing but minus ln P1S by P10 equal to minus 1 by x2 as earlier, as we have derived them earlier, and this is after expansion and neglecting the higher terms, it is almost equal to x2. So in place of x2 we can put this overall value, because x2 is nothing but equal to this one. So x2 has the expression delta H of fusion by RT square into delta TF. And finally we get equation number 3, where we are getting the expression of delta TF, that is the depression of freezing point. So the expression of depression of freezing point is delta TF equals to RT0 squared by delta H fusion into x2. Now likewise the previous expressions, let's get try to get a constant like Kb. Here x2 is nothing but m1 by 1000 into m, because m is the Molal concentration. Okay, and m1 is the molar mass of the solvent. So easily the relationship is very simple. x2 is m1 by 1000 into m. We know that, and putting this value in equation number 3 we get this relationship. In place of x2 we can put m1 by 1000 into small letter m. So in terms of molality we get this relationship, equation number 4. So we get the constant Kf. This is called as cryoscopic. This is known as cryoscopic constant or the Molal freezing point depression constant. Okay, and the value of Kf is very simple. This overall term is the value of Kf. So we have the expression of Kf. Before that we blocked equation number 4 and express Kf and then finally block them. So here is one mistake. The m should not be here. Let me correct it. M should be absent here. The m actually m is not here. Okay, so m is not here. Look, this is the expression of Kf, which is RT0 squared by m1 divided by 1000 into delta H of fusion. So this is equation number 5, and let's block it. Okay, and a few points on Kf. Kf is also known as the Molal freezing point depression constant or the cryoscopic constant. It is a constant at certain pressure, because at constant pressure freezing point is also constant. Likewise the previous statements. And Kf is a function of molar mass of the solvent, which is constant for a particular solvent. The same. And here the physical significance. So if you put 1 in place of m, small letter m, in the equation number 4, then you will get delta TF equals to KF into 1 equals to KF. Therefore, what is KF now? KF is the freezing point depression of a 1 molal solution. Okay, and we have not found the just determined the dimensional unit as we have done it in case of Kb, the same process. So the result is the dimension of Kf is same, theta into m into n inverse, and the corresponding unit is Kelvin kg per mole. Okay, and approximations all the same. Statement 1 is same as Kb, statement 2 is same. Just in statement 3, in place of liquid we have to add solid also. So for solid or the liquid, here vaporization and sublimation. Okay, this is the little bit change. All the other things are same, and the 4th statement is also same. So that's all about depression of freezing point. Thank you. Have a nice day.